Hey, so we're in chapter 8. This is probably one of the biggest ideas that we're going to be talking about. So, in chapter 8, what we're going to be talking about is essential ingredients for a hypothesis test. So, in this chapter, we're going to be talking about how do you test a hypothesis that has to do with percentages. Okay? So, let's say that we spin a coin 20 times and 20 times we get heads. What do you think about this? Do you think the coin is fair or unfair? What would happen if instead we got heads 15 out of 20 times, or about 12 out of 20 times? So which one lines up more with our expectations of a fair coin, and which ones line up more with one that would say unfair? So whenever you're doing a hypothesis test, here's the setup. Before we go through these, a lot of you know about the scientific method. So in the scientific method, what you do is that you come up with a hypothesis, then you test that hypothesis, and then you come up with a conclusion. That's a lot like what we do, and this is what they use in a lot of science as well to back up their claims. So first, you state a hypothesis. Okay? So this is a claim about the world. So in the above example, we hypothesized that a spun coin is the same as a flipped coin, so that it would be fair. What would the counterclaim be? It would be an unfair coin. The next step is that we talk about our preparation. So in science, what we do is that we determine how we're going to gather the data, how are we going to make a decision, and we want to make sure that we have enough data to minimize the probability of making a mistake. So if you only flip a coin once, that doesn't really tell you enough. You have to do it a lot, but we have to determine how much is a lot. The next step is that you actually carry out what you prepared to do. Okay, so you collect your data, and then you compare them to your expectations. So we would expect to get 50% heads if we flipped a coin. Okay? So if we flipped a coin, and let's say that we got heads 45% of the time, we compare that to 50% and see, well, is it that much different to back up the claim that the coin is fair or unfair? The fourth step is that you state your conclusion. So you kind of write up a summary about what your hypothesis was, and what the data actually showed you. So the main ingredient we have is we actually have a pair of hypotheses. So in the example we talked about above, we are going to use this to formulate our hypotheses using statistical language. So our first claim was that the coin would be fair. This is your natural expectation. What we call this is that we call this the null hypothesis. Okay, so the null hypothesis, which we also call H naught, which we denote with this little, looks like a 0, is what we expect. So we expect the proportion of heads to be 50%. So this is the same thing as saying heads 50% of the time. Okay, so the null hypothesis always follows a certain formula. So the null hypothesis is always going to be one of these three things. It is the theoretical probability. Okay, so theoretically we would expect to get a coin to come up heads 50% of the time. It can also be the status quo. Okay, or it could be previously gathered statistics. So let me give you an idea of what status quo could be. So status quo could be that we expect the population to be made up of 50% men and 50% women. That's the status quo. That's what we've been led to believe. But maybe that's not true. Maybe there are things that are affecting that, like war or some sort of disease that affects one gender versus the other. Previously gathered statistics is when we want to know, have things changed over time? So for example, if we wanted to compare, say, the percentage of college graduates in 1940 to the amount of college graduates in 2020, okay, maybe they're only different by like 0.5%, and we want to know, is that statistically different enough to say that college enrollment rates and graduation rates have changed? So it depends on the context, whether we're looking at the null hypothesis as being a theoretical probability, a status quo, or previously gathered statistics. And we'll talk about how to identify those a little bit later. Now, the alternative hypothesis is what we think has changed and how it's changed. So if a coin is not fair, what that means is that it's not going to come up heads 50% of the time. So it won't come up heads 50% of the time. Maybe it comes up more tails, maybe it comes up more heads, but it's not going to be an even split. Okay? So note that a hypothesis is always made about the population and not about the sample. So what we do is that we use the sample later to decide which hypothesis we side on. So I like to say that the alternative hypothesis is the test or the expectation. Okay, so when we're looking at this, we have three different kind of hypotheses that we can consider. One is called a two-sided hypothesis. That's where we think the population is just not equal to the new population. Okay? Or we just think that they're different, but we're not sure how. The other alternative hypothesis is that the new population is less than the old population. Or the new population is greater than the old population. So, just a couple examples of these. This could be a coin being unfair. So an unfair coin. This one, if we're looking at a population that is less than the old population, that could be child mortality. So child mortality has decreased in years, so it's a lot lower than it used to be. And for one that's higher than what it used to be, we could say female college graduates is higher than it used to be. Okay? So, let's look at an example, and something to note is that P is the population, so the one that we're thinking something about, and P naught is the value that we're forming our hypothesis around. So P is the unknown value, and P naught is the test value. And remember, P hat is our sample. So let's look at an example and we'll be marking these. So, an experiment is done with criminals released from prison in a certain state where the recidivism rate is 40%. What recidivism rate is that is 40% of prisoners return to prison within 3 years. So, 100 random prisoners are made to attend a boot camp for 2 weeks before their release, and it is hoped that boot camp will have a good effect. What we want to do is write the null and alternative hypothesis regarding the recidivism rate of the inmates that attended boot camp. Okay, so a couple of key things to point out is that the status quo, or the previously determined recidivism rate, is 40%. Now, what we did for our experiment is we collected 100 random prisoners and had them attend a boot camp for 2 weeks before their release, and the hope is that boot camp will have a good effect. So, our null hypothesis is that boot camp isn't going to have an effect, so we're still going to have a 40% recidivism rate. So, boot camp has no effect, and recidivism will still equal 40%. So we're assuming that nothing will change. Now, the alternative hypothesis, or what we're hoping to happen, or the test value, okay, is we're hoping that boot camp will have a good effect. So we're good people. What we want is that we don't want these people to return to prison. So we're hoping that the population is less than that 40%. So boot camp has a positive effect and the recidivism will be less than 40%. So that would be our status quo. So we assume that our test is going to do nothing. And then the alternative hypothesis is, hey, we hope it makes it less. Okay, notice I didn't use any p-hats here. The reason I didn't use any p-hats is because you don't use p-hat until after you've collected your data. So you should always state your hypothesis before you collect your data or your sample. Otherwise, it's unethical. Now, a coin is flipped, okay, 30 times, and it comes up heads 18 times. What we want to do is test the hypothesis that the coin does not come up 50% heads in the long run. Below is an incorrectly stated hypothesis, and we want to rewrite it correctly and also note what was wrong. So go ahead and pause the video and rewrite this and tell me what was wrong. Okay, so here's what's wrong. This p hat is not what we're using. We want to say something about the whole population or all coins that we're looking at. So we say p equals 0.5. The alternative hypothesis is always related to the original value. So the alternative hypothesis should be that p does not equal 0.5. Now, one of the big things is that we are always comparing to p naught, okay, which should always be 0.5 for both H naught and HA. The other thing that went wrong is that p hat should not be used or found until after we state our hypothesis. So, if we flip a coin 30 times and 18 times we get heads, that's 60%, and that should not have shown up in our hypothesis. Okay, so a couple more things, and then we're going to talk about these in a little bit greater detail in the next video, is what criminal trials have to do with hypotheses. So in criminal trials, we have two hypotheses that are placed before a jury. We either say that a person is not guilty or guilty. We never say that a person is innocent, okay? We say a person is not guilty because we haven't found overwhelming evidence that they are guilty, okay? So what this means is that these two hypotheses don't hold the same weight, okay? There's not a 50-50% chance that you're not guilty or guilty. Okay, usually you're only guilty if you have found overwhelming evidence that proves the contrary. Okay, so the same is going to hold for statistics and a hypothesis test. So, here's the deal, is that the null hypothesis always gets the benefit of the doubt. Okay? That is, it's not until the very last step that we say that the null hypothesis is probably not true until we get extremely unusual evidence to reject it. Now, just like the criminal justice system isn't perfect, neither is statistics, we might make a mistake, right? So one mistake you can make in the criminal justice system is that you could say, hey, this person's guilty when they're actually not guilty, or a person is not guilty when they are guilty. So one of those mistakes we want to say is more likely to happen than the other. That is where something called the significance level comes in, which is called alpha. What this is the probability that we accidentally make that mistake of rejecting the null hypothesis when it's actually true. And usually, we only want that to happen if there's a 5% chance of it happening or less. Okay, so if this was a criminal trial, I only want to say you're guilty if I'm 95% sure you're guilty or more. Okay, that means that I only want to say you're guilty if there's only a 5% chance that you're not guilty. Now, sometimes, depending on the statistics, we might make alpha very small, so 1%, especially if we're doing like a health-related survey where we could be saving or ruining lives. Or we can set it as high as 10%. So if we're doing something that just has to do with public opinion, Okay, maybe the stakes aren't as high or there's a lot more room for human error, so we make that 10%. So we're going to stop this here and we'll continue this on in the next video.